Okay, welcome back everybody to the second part of this morning session. Our next speaker is Yelena Guryanova, and she's talking about time-symmetric formulations as a tool to understand causal non-separability.
Thank you for the introduction, and thank you to the organizers. It's a wonderful conference, and I'm having a great time. So in this talk, I'm not going to talk concretely about one work, but I'm going to talk about many different works. And I'm also going to maybe be a bit provocative. So Esteban was telling me yesterday that there's not enough discussion in the audience and opposition. So I'm going to stoke the fire a bit maybe and encourage some of that. The theme of my talk then is this, somehow how we can understand causal non-separability from a time-symmetric formulation, which may seem a little counterintuitive. As you see, I've done my presentation on the iPad, which is a first for a talk, so let's see how that goes. So the outline then is going to be a short recap of what I mean by the time-symmetric formulation, or rather what people 50 years ago meant by it, and in particular two-time states, or the two-states formalism, as some people know it. Definition, how you create these states in a lab, experimentally, things like this. And then really my talk is focused more on correlations, the type of correlations that these states can produce, and what we can learn additionally by doing, let's say, calculations in this formalism, because there are new things, new theorems that one can write down. And finally, I'll conclude with a flavor of the future work that's going on in Vienna at the moment, and wrap up with some conclusions. Okay, so what is the time-symmetric view, or the time-symmetric formulation of quantum mechanics? So I have these two columns, and on the left-hand side, I have what everyone is used to, which is quantum theory. And in quantum theory, you have states in the Hilbert space, well, rays, so to speak, and they, let's say this ray lives at Alice's time t1. You don't have to associate a time to it if you don't want to, it's just a Hilbert space. In the two-time state, or the two-states formalism, you postulate that the basic element of your theory is not a ray that's going a ket, but it's a ket tensor product with a bra going the other way. So, in the two pictures then you see, here you can interpret the state psi2 at time t2 in two different ways. So you can interpret this element of your theory as a fundamental post-selection or an experimental post-selection. What does this mean? So fundamental post-selection means that this psi2 is hanging around there waiting and it's guaranteed to happen. Or you can interpret this state as a fundamentally post-selected state. You start in the state psi1, and at some later time, you project onto the state psi2. But the only difference really that you need to appreciate is that in the right-hand picture, your states are these rays, and in the left-hand picture, your states are these rays. That's about it. And okay, to continue this comparison then, the probability then you associate, I'll show you how you build the probabilities in a second. In quantum theory, the probability of some outcome A, given measurement setting X, is conditioned on the states, right? It's states dependent. But in the two-time states formalism, it of course depends what you do at a later time, right? It depends on this states or this post-selection psi2. So the operational description of the probability is as follows. In quantum theory, you start in the state psi1, and you ask, what is the probability to obtain outcome A given measurement setting X? In this theory of two-time states, you start in the state psi1, and you ask, what is the probability to obtain the outcome A given the measurement setting X, and that you succeed in obtaining psi2 in the end? So that's the equivalent reformulation, if you like, of the probabilities. Okay. So this two-time states that I showed you, this basic element in your theory, the ray in your theory, I showed you was a product state, right? It's psi1 tensor product psi2. And of course, you can write down a natural generalization where the times at t1 and t2 are are entangled, right? So at Alice's, I switched between calling the Hilbert space A in and A out to help people think about process matrices.
For the audio quality, can you please stay close to the camera?
Oh, but it's...
The audio gets worse.
Okay, sorry. Right. But of course, from the product state, there's a natural generalization to two entangled states between these two times. And just a short note on normalization. So there's a natural way to define normalization in this new theory of two-time states. And it's to correctly basically contract bras and kets. So if your initial preparation and post-selection are correctly normalized, then, or normalized to 1, let's say, then your two-time state is also normalized to 1. You just have to keep track of the Hilbert spaces and contract the correct Hilbert spaces together. So A in bras are contracted with A in dagger, kets, and so on. So the normalization isn't a problem. Okay. So what are these two-time states? So, okay, there's this idea that they're fundamentally post-selected, but you can also create them in the lab. And in fact, you can herald them in the lab following a prescription that's universal probabilistic. So, sorry, sometimes people say, yes, two-time states, that's just post-selection. For me, that's a bit too hand-wavy because, yes, okay, for example, if you have two lists of, let's say, grades that you get in a class and you're asked to post-select on the students who got 100%, it may be students 30 and 50 in list 1, but it may be students 2 and 3 in list 2. So the function that you apply to these two lists in order to post-select on the students that got 100% is different. That is not universal, right? I have to check the list first and then cherry pick the answers that I want. What I want to say here is that creating a two-time state is universal probabilistic in the sense that there exists one algorithm for any state. So if you get given a black box, you are able with one universal algorithm to create the two-time state, probabilistically. So in practice then, how do you do it? We're going to start from the bottom up. If you want to create a two-time state of this sort, so let's say a two-time state like this. This is a one-party two-time state, just on Alice. How have I written here? IJ, right? I tensor J. Alice at time 1 or input and Alice at output. How do you do this in the lab? Firstly, you start with a system and ancilla, and you prepare this system and ancilla in the target state that you want, right? So these two things are identical up to some transposition, and we know how to prepare this state in the lab, right? Step 2, you perform your measurement. This should be an M measurement. M, A of X, I don't know, spin Z, spin X, any measurement that you like depending on your system. And you do nothing to the ancilla, right? This is captured here. You don't touch the ancilla. In step 3, you project onto the maximally entangled Bell state. So you do a Bell state measurement, and you hope to get the outcome corresponding to, if it's a qubit, 0, 0 plus 1, 1. Or if it's higher dimensional, you hope to get this state. And in the end, what you do is you ignore the ancilla, you trace it out and throw it away, such that the statistics that you get, which are these ones here, would be identical to having had a two-time state in the beginning. So this prescription is universal in the sense that, okay, it's not guaranteed to always occur, this post-selection. And, okay, in some sense, it's exponentially bad, but at the same time, I've never done the calculation to check whether if you average over the Haar measure of what states you expect after the measurement, how successful your post-selection is going to be. Most likely, it's maybe better than exponential. So this is the picture in the lab then. So to create this two-time state here, with some measurements in the middle, I have this well-defined, time-ordered prescription in the lab. This is for one party. Now, the next generalization is from pure states to mixed states. So the states I just talked about was pure. How do you create mixed states? Well, you just combine many pure states like this in a mixture, in a probabilistic mixture. And you build the theory exactly like this. Indeed. So on the next slide, how do we build the theory? So we've discussed rays in the Hilbert space, but as we know in quantum mechanics, we don't compute probability amplitudes and things with rays. We need to use the density operator. So in quantum theory, how do you construct the density operator? The density operator you construct as follows, right? So you take a probabilistic mixture of pure states which is the ray tensor product with the ray in the theory dagger. In exactly the same way, you're going to do this for 2-time states. So you take a probabilistic mixture of a 2-time state tensor product with the 2-time state daggered. And what you find is when you run through the calculation, the 2-time state that you get at the end, which I've called here eta, is identical to some regular bipartite quantum state, but with the output spaces flipped. So this A2 could also be an output space. Doesn't matter. So it's the output space in this theory is transposed in some sense. But otherwise, the construction is very similar. You postulate your rays, you define how you define the density operator, so on and so forth. All is well. Okay. Another way to think about 2-time states, which will motivate the discussion for correlations in the rest of the talk, is as tensors. So in this picture here, this is a single-party 2-time state, let's say on Alice. And it's just a convex combination of pure 2-time states, right, as one would expect. And you can rewrite it, you can manipulate the tensor products, because in practice, we never write the tensor products when we write the states, right? A bipartite state here is constructed in exactly the same way as the single-party states, but you can have entanglements now between Alice in, Bob in, and Alice out, Bob out. And then I construct the density operator, eta, in exactly the same way. I have some convex combination of pure bipartite 2-time states. But this is just a matrix, right? At the end of the day, it's just a matrix of numbers, and it's a matrix of numbers, or in fact a tensor with 8 indices, right? Because I have 8 Hilbert spaces. I have the Hilbert space of Alice in, Alice out, Bob out, Alice in dagger, because I had to construct the density operator, Bob in dagger, and so forth. So I have some object, some matrix with 8 indices. And it's very useful when you consider this object to consider it in conjunction with the link products. The link product is just a way that tells you how to consistently contract indices and take the trace. So, for example, if I wanted to take the trace, or trace Alice's input space out of this bipartite 2-time state, I would contract it by taking the link product with a tensor of 1s. So this is the link product. It tells me to match the correct Hilbert spaces with the bras and the kets, and the daggers and non-daggers, and these are the indices that I have remaining. So the point here is that one can define everything consistently. In quantum mechanics, these indices are always traced out in pairs because we have an input space and the daggered space as well. Okay. So, moving on to how to define probabilities. So now we have a theory of 2-time states, and we want to define how we get probabilities in this theory. The probabilities I'm going to discuss are going to be under quantum operations. So the idea here is that because you have this sort of intrinsic post-selection, fundamental or experimental, depending on how you interpret it, that to generate the probabilities, you have to use Bayes' rule. So the probability of obtaining outcome A given measurement setting X, and you have this 2-time state eta, is given here by Bayes' rule. So you need to renormalize based on the success of the post-selection succeeding, right? This is, you have to post-select on the success probability of the final state, psi 2. Equivalently, you can write this in terms of a link product with the choy of a CP map. So I haven't written it here, but maybe I'll write it. The choy of some quantum map on Alice is defined in the usual sense, 5 plus. And then you can define everything with the link product. But you have this renormalization in the bottom. If you go to 2 parties, everything is exactly the same. The link product is also takes care of different Hilbert spaces, right? So in principle, I could write here a tensor product, but I don't need to. In the bipartite setting, it's no different to the single party. Indeed. This line here is just to tell you that in the choy, this is the choy of the quantum maps, right? Choy of map M. there are some hidden Krauss operators, right? So if you were to write this state out, as I had done before with pre and post selections, the Krauss operators get sandwiched in between different parts of the state. You don't need to know this, but if you're interested, okay. So, of course, because we have this renormalization, the probabilities generated by these two-time states are nonlinear with respect to the states. This means if I take the probability of outcomes A, B given measurement settings X, Y with respect to some state E to 1, and the same with respect to some state E to 2, and I mix them convexly, that's not the same as taking the outcome probability on the convex combination of the mixed state. Okay. Okay, before I continue, so this rule here, this probability rule, was first defined by the ABL rule, the time, symmetry, and quantum processes of measurement, and we later generalized it to completely arbitrary two-time states, so really these mixtures of pre- and post-selections. So one thing that it's possible to say about two-time states is that all bipartite process matrices are, in fact, two-time states. So here I have on the left, I have a picture of two-time states. So I've written T for tensor, because I like to think of them as tensors with a link product, and eta for two-time states. So these are all the positive two-time states. And some strict subset of them corresponds to process matrices. What does this mean? Okay, this means that a world with indefinite causal structure, such as the world of process matrices, is equivalent to a world with fundamental post-selection, which is a quantum world with independent initial and final boundary conditions, which are guaranteed to occur, as opposed to post-selection, which occurs probabilistically. What this also means is that under quantum mechanics, all process matrix correlations can be simulated in the lab universally probabilistically. So I have the same recipe each time in order to create these probabilities. And in fact, what one can show is that there is an isomorphism between the set of bipartite process matrices and two-time states. Okay. So what are process matrices? Well, we've heard a lot about them already. I'll just recap very briefly. Process matrices are states or objects in a Hilbert space. Positive, they have some particular trace and some linear constraints, which appear in this pink bubble. This thing here is defined as trace and replace, so trace of X. This is the trace and replace operation. So the interesting question here is then which class, if we find this isomorphism, which class of two-time states correspond exactly to these bipartite process matrices? And the answer is to do with probabilities. So on the left-hand side, I have written the formula for generating the probabilities for an arbitrary two-time state, something positive. So I take the tensor product, the link product with the choice of the maps, MAX and MBY, and I renormalize in the bottom based on the success probability of the post-selection. This is CPTP at the bottom, because I sum over A prime and B prime. On the right-hand side, we have the well-known process matrix probability formula, the probability of obtaining outcomes AB given settings XY, given that you have a process matrix, is given by this trace formula, which I can also rewrite in terms of a link product if I transpose the output spaces of the Choi maps. Right, so here there's a slight difference between the above. I've transposed the output spaces and introduced the link product so I don't have to take the trace. This is convenient for me because I'm going to compare this now to the two-time state probabilities. The two-time states, which turn out to be process matrices, are exactly the two-time states for which the denominator in the formula for the probability is constant for all CPTP maps in quantum theory. This constant is equal to exactly 1 over the dimension of the output spaces of Alice and Bob, right? So the trace of this E to W is dA out, dB out, which is exactly a process matrix. So this establishes the isomorphism. dA out, dB out. Okay, so these objects are identical up to some transposition of the output spaces. Okay, that's maybe not terribly interesting. But what is perhaps more interesting is that, in addition, when one knows this and one works in the kind of formalism of two-time states, one can derive additional constraints. So the constraints I showed you before for process matrices were these ones here, right? These are the necessary and sufficient constraints, and also positivity and trace. But these are the linear constraints, right? Using the formalism of two-time states, one can derive additional constraints. So to derive these constraints, typically what one asks is that the probabilities are positive and they behave sensibly in the sense that they're normalized. And in the process matrix world, people start with this equation here, right? They want that... Oh, I missed a sum. I apologize. It's the sum over A and B. And the sum over A and B is 1. This is for a CP-TP map. So the trace of a process matrix with some CP-TP maps, M of X and N of Y, is 1. I'll put the sum back in here too. This is maybe the advantage of having an iPad. Okay. This I don't need because I've normalized everything correctly now. Fine. What one can show this actually implies are these 3 additional constraints. Now, you can write them in terms of this link product with CP-TP map C, C tilde, N, M, D, D tilde, and so on. Or you can rewrite it, if you like, in process matrix notation. In the following way, but I will illustrate this with an example because this looks terribly complicated. So let's look at the first constraint, this additional constraint that one gets when one looks in the two-time formalism a little bit at process matrices. This first constraint tells you the following. It tells you, and this is the graphical representation, if I take a process matrix, and I've deformed this process matrix, right, but it's the same object, and Bob applies some CP-TP map, or in fact the choy of a CP-TP map, between his input and output spaces. So this thing gets completely contracted. And Alice applies a CP-TP map at her output space with some output space tilde. So this is why it's useful to think about times, because Alice is applying on the left-hand side this CP-TP map C between times A out prime and A out, if you like. This state, and this is a state in the end, is indistinguishable from if Alice were to perform a different CP-TP map between her times A out prime and A out. This is a C tilde here. This is a generalization. Let's see if I have this slide. Indeed, this is a generalization of the trace and replace condition, right? Because if the CP-TP map were the identity, and N were also the identity, you would recover the known results here, the known characterization. But this is more general because it holds for all CP-TP maps. So in fact, the characterization on the left doesn't imply these new constraints, 1, 2, and 3, and 1 is the one I've illustrated here. And what this tells you is this already gives you an idea about the causal structure a little bit in this process. It says that on the level of states, it doesn't matter what Bob does. And indeed, I could have, drawn Bob much higher up in this process. Usually people draw them in parallel, but it doesn't have to be that way at all. I've just drawn it in this scenario to sort of make it look more extreme, that whatever Alice performs in the future of a potential measurements here is not going to influence the state at all. And this is something that, this is like a new property that one gets from the two-time formalism. And you get a whole host of these conditions. And in fact, what it does is this generalizes chase and replace to all CP-TP maps, generalizes. The trace and replace to arbitrary CP-TP maps. Okay, that's kind of nice. That's what we learn by using two-time states as a tool, right? Okay. I've been here. Okay, so the question now is, what other properties do linear two-time states, also known as process matrices, have? So far we've learned that they're linear in the probabilities under quantum operations, and we can derive these additional channel properties for them. But how much further can we go? So here is a property. Oh, this is a NOTS property. Right? So unfortunately, let me write this in red. This is sad. This is a non-composition of process matrices or linear. They don't compose, and this is sad for many reasons. So Marius told us yesterday, he gave us the reason why they didn't compose, and I'll talk about that in a second. But what this means is that if you take a process from the set of, use this color. If you take a valid two-time state, which is a process matrix, and you combine it under tensor products with another one, what you end up is something outside of the set. It's still positive, of course, because you have two positive operators, but it takes you outside of the set of process matrices. They don't compose. What Marius told us yesterday, and as far as I interpret his talk, is that they don't compose under any operation. So if you think of some reasonable assumptions that you want your operation to satisfy, like being bilinear and things like this, then it's still not possible to compose them. And the only processes that are composable are what I call same-way signaling processes. So this is something that was known by me. The bottom of my my reference here is missing, but actually here I also wrote that Villacini and, I write it. Villacini and Renato also knew about this. Villacini and Renato. Renner, and I think Ralph Silver did some work on this, but it's pretty well known that if you take two, what are these? Process matrices, right? In the world of process matrices, under tensor product, they don't compose. Under any reasonable operation, they don't compose. And the only ones that do are the ones which are same-way signaling. So A to B composed with another A to B. One way that I like to motivate this is in the following way. So if I take two process matrices and I compose them under a tensor product, and process matrices are also two-time states, so I'm taking 2 points here again, I have this sort of 3D thing here. And in order to derive what people want, of course, is that the probabilities are positive and that the sum over AB of the trace of MAX tensor MBY, I have an N, sorry, NBY, and maybe I'll write a tilde here because this is really on the full space of W1 tensor W2. You want this equation to hold. And when you demand this, what you're asking for is that you look at the most general measurements which are non-local in space-time. So this N, which connects, which Bob is doing locally in Bob's part of the space, connects his input space with his output space, but also his input space with his output space primed, which could in principle be at a different time, right? These things don't have to be parallel, the two processes that you take. And yet there was this assumption that there is a local causal order in the labs in process matrix world, right? So somehow this violates a little bit that assumption because here I have to consider the most general measurement, which is non-local in space-time. So that's sad. Process matrices don't compose. And here I come to the provocative parts. So what does this mean about tabletop experiments? And this is something that I don't really understand. So if I have something that's a genuine process, it doesn't compose, right? I shouldn't be able to put them together. But if I have a tabletop optics experiment, Yes. If I have a tabletop optics experiment, then I could in principle compose them, right? By wiring the two tables together. So this theory is fundamentally non-composable. So I'm interested to know how this is explained in the lab, because what it seems like is that some time-like parameter in process matrix world is mapped to a space-like arm of an interferometer, which may constitute cheating on some levels. I don't know. I would be interested in hearing your thoughts on this. Okay, so now, yes, indeed, now that we've talked about these correlations, one way, so what have I talked about before? What's this? The non-compositions. Okay, so I've talked about states a lot, but now I want to talk about correlations, and in particular correlations under quantum mechanics. And in order to talk about correlations in some framework, I need to characterize their strengths a bit. So how do we assess the strength of correlations in the causality paradigm? And my go-to game is the Guess Your Neighbor's Input game. It was defined in this paper in 2010. And the Guess Your Neighbor's Input game goes as follows. Alice and Bob are space-like separated, space-time-like separated. They can be any like separated you like. And Alice has some classical input X and some classical output A to her black box. Bob has some classical input Y and classical output B. X and Y in this game are uniformly distributed, and the aim of the game is the following. It's to guess your neighbor's input. So Alice has to guess Y, and Bob on his output has to guess X. If they get this correct, then they win. And in the bipartite scenario, when all of these inputs and outputs are binary, zeros or ones, then this functional is assessed in the following way. It's a quarter times the probability of 0, 0, given 0, 0, plus 0, 1, given 1, 0, and so on. There are only 4 probabilities that you need to compute from your correlations in order to see how well you've done in this game. Now, the maximum probability of success is algebraically upper bounded by 1. And, okay, there isn't just one correlation that does this. There is a family of 4 correlations because Alice may have to guess not Y, and Bob may have to guess not X. And so there are 4 different distributions which you can parameterize in this way here. So this is going to be my assessment of the strength of the correlations. Interestingly enough, a general 2-time state can reproduce these great, fantastic guess your neighbor's input correlations under quantum measurements. Here is the state, and here are the Choi operators in terms of the Choi operators with the Krauss on the left and the right. You don't need to, you can go through this example yourself, but what you will find is that you can generate the guess your neighbor's input probabilities. So importantly, this 2-time state is not a process matrix, because we know that process matrices cannot reach the algebraic upper bounds of 1. They have some notion of more than one-way signaling, but less than perfect 2-way signaling in them. So in the space of correlations then, how does this look? So on the left-hand side, I have my picture of 2-time states, the positive ones in the light purple bubble. A strict subset of that are those 2-time states which are process matrices. And on the right, I have the space of correlations, which I get when I map from map under quantum operations. So as well as being able to show that some 2-time states can get perfect guess your neighbor's input correlations here, you can actually show that a 2-time state can get the entire hypercube of correlations. They can achieve everything under quantum operations. Process matrices under quantum mechanics get process matrix correlations, and these violate what are these causal correlations, right? So here there is a point which actually touches the causal correlations touch the process matrix correlations. Causal correlations are those which can be decomposed in the following way. Some P of, well, it's Q, signaling A to B plus, exactly as Eamon defined in his talk previously. And we know that there are points which touch the sets because of Cyril's work. So this is the advantage. I can reference somebody live, Cyril Rancière, who looked at the maximum violation of process matrices in a setting where you have qubits, and they found that there are points which violate the causal correlations because there are known classical bounds for these hyperplanes, right? Okay. The next natural question is, now that we've considered quantum operations and how they map to the space of correlations, what if I consider other operations for general 2-time states and the subset of 2-time states that corresponds to process matrices? What other correlations is it possible for me to get? In order for me to talk about this, I need to introduce this notion of backwards in time signaling. Here I reference Časlav at some conference, sorry, and Giulio Chiribella, Giulio Chiribella, who also had similar ideas. Or Giulio, sorry. And the point is as follows. You first, this no backwards in time signaling thing is going to allow us to talk about, define extra hyperplanes in the space of correlations. So what do? You first give you're in this black box setting, device independent, and you're instructed to first give the output and then perform the input. So this party here must first give the outputs A, and then an external referee tells them to perform operation X. Now, we say that this correlation, this local correlation, is no backwards in time signaling if the probability of A given X is independent of X, independent of what happens in the future. In quantum theory, this is kind of obvious because you can think of this as two sequential measurements, the first with a fixed measurement and the second as a unitary operation. So the first fixed measurement has a bunch of outcomes A, but the second one doesn't have any outcomes, right? And this probability is clearly independent of any unitary transformation, this is X here, that you may perform at a later time. The story becomes more complicated when you have two parties, and you can define a notion of no backwards in time signaling through these constraints here. So there is no backwards in time signaling if Bob's local distribution, probability of B, which happens here, doesn't depend on the Y that comes later. So this is independent of the inputs that the referee gives in the future. It could, of course, in principle, depend on Alice's inputs X. And the same holds in the comma. So this is exactly like in the no signaling scenario, in the Bell scenario, with X and Y flipped, if you like. So the same hyperplanes with X and Y flipped. There are, of course, exist structures that satisfy no backwards in time signaling that are more complicated. And this is what we're going to explore. So we now take this framework, this two-step procedure, and apply it to a set of states and operations, and we check to see if these correlations satisfy the no backwards in time signaling principle. So what I do is I take a state from the set of two-time states, and in particular I take a process matrix. I apply this two-step procedure, which is now a restricted operation. This is some fixed measurements MA followed by CPTP map UX, which is less general than what we had before. And I generate correlations in the following way. And I ask, does this correlation satisfy the no backwards in time signaling principle? Oops. I did turn the page. I'm not able to. Let's do like this. And the answer is yes, indeed, they do. And the surprising thing is that they actually correspond to causally separable correlations. So one can show that the sets of correlations under this restricted class of operations from the world of process matrices is mapped to a measure zero hyperplane in the space of correlations. These are all causally separable correlations. And this is if and only if. And in doing so, we've managed to also characterize this guess your neighbor's input point, this winning correlation in the guess your neighbor's input game. It occurs as a vertex of the polytope of no backwards in time signaling polytope, or hyperplane, if you like. So before I had this loose point hanging around, and now I've managed to capture it under a restricted set of operations. So the question then is that, so this is a summary then, right? This is something else. I have many slides that are the same thing. So what other properties do two-time states satisfy? So now we have a list. They're linear in the probabilities. They have these additional channel properties, which we learned from this two-time state formalism, and they satisfy this no backwards in time signaling constraint under a restricted class of operations. One can show that all of these properties imply one another. So in particular, what this does is this singles out process matrices in the space of two-time states. In space of two-time states. So before I just showed an isomorphism, but now under some theorems, I'm able to single them out given various properties. I don't need to say, these states are equivalent under isomorphism. I can single them out via a bunch of conditions. And this is useful. So, yeah, indeed. So this is useful because it allows you to answer other questions. So in particular, to give you a flavor of the future work that's going on with Jessica Barbarescu, Eamon Beimler, and Constantino, is does there exist a set of tensors? They don't necessarily have to be positive, but tensors, because remember, we can think about two-time states also as tensors and contracts with operations under a link product. Does there exist a principle or some reasonable definition under some set of operations which approximate the process matrix correlations? So are we able to approximate the process matrix correlation set by applying some reasonable class of operations to some well-defined set of tensors? This is somehow the question we want to address. So to conclude then, what we've done is we've taken the two-time state formalism, we've used it to help us understand theories with no global causal order, and we've been able to derive these new results. We found that linearity in probabilities implies global causal order and this idea of no local loops or backwards in time signaling. So a related question is, can one find other sets of two-time states and other measurements that are also linear? Because it could be that under quantum mechanics they're linear, but also under some other more exotic operations you also find a set of linear, of two-time states which are linear in the probabilities. And then finally, okay, I wanted to touch on this idea of experimental versus fundamental post-selection versus current experimental setups, given the fact that, okay, these process matrices, two-time states, they're not fundamentally composable. And yeah, with that, I'd like to thank you.
Thanks, Yelena, for your talk. Questions? Okay.
It's just a comment on this wiring in the experiments and like impossibility of creating tensor products. But nevertheless, it seems like you can do something in the lab. But in fact, I'm not sure you can do it. But what you can do maybe is, it was remark from yesterday, you can maybe put two switches on the top of each other and then have Alice lab that would take a particle from the both switches. But then I would define the process in the tensor product always such that Alice acts on two particles, not on one. And then you see that if you have these switches on the top of each other, sometimes you will have in some time intervals only one particle on Alice side, and in some time intervals two particles. But when you act only on the two particles, you will really then kill all non-allowed terms, and you will get again allowed process messages. So
but how do you guarantee that how do you show that you're acting on two particles and not?
No, but for example, if in the switch, if both of them at the same time go to Alice, they will come at the same time interval. But if in one switch it goes to Alice and the other switch to Bob, then they will not come to the same time. So what I want to say is that somehow nature thinks about that, and when you act on both particles, it will subselect only the good parts. I don't know, I don't have a full understanding, but at least in this example, it matches with a theoretical expectation. Yeah.
Mm-hmm. Okay, it'll be interesting to discuss, yeah.
There was some question there, then you, and then you. Okay.
There are a lot.
Oh my God. I'm not sure we can take all the questions, but...
Okay, yeah, thanks for the very nice talk. Yeah, just a little comment. Something around this was kind of remarked yesterday as well. There is a sense in which you can think about composing process matrices. So there's a paper by Alex Kissinger, where they can compose these process matrices, but like the space of things they're allowed to act on is restricted to essentially.
I don't know the paper, unfortunately, either.
Okay.
Sorry.
Well, yeah, okay. So I was going to just mention it, and I was wondering if it might be a way to describe what's actually happening when you put two optic experiments next to each other. But, no.
Yeah, I don't know. I'm sorry. It would be interesting to see. Yeah.
Yeah, no worries.
Okay, then down there, and then you. do we still have time for 2 questions, or shall we? Okay, good. There are.
Yeah, thanks, Yelena. So can we, on these 2 time states that go beyond process matrices, can we have some entropic measures? So there are 2 reasons. Of course, we have entropic inequalities for the causal inequality from Cyril and others, and we also have some ideas from ordinary quantum mechanics that, let's say, PR boxes actually don't violate entropic inequalities. So it would be nice to have some entropic measures of correlations on these 2 time states that go far beyond, so to see if that's analogous or not analogous.
I have no idea. I've tried to define a notion of entropy for process matrices, but I was somehow unsuccessful. I guess it's a theory somehow. I mean, I looked into things like the Halevo bound of signaling, and I tried to define the entropy of parts, but I wasn't able to get anywhere. So I'm interested, but I don't know how. Yeah.
There was one more question there. But yeah.
Okay, just 2 quick questions. Thanks for the talk, Yelena. The first one is just clarification. I thought that the set of process matrices was the set of linear 2 time states, but you are saying that there might be other linear. I'm a little bit confused.
Under quantum operation, so okay, there's process matrices are isomorphic to a set of 2 time states. Which 2 time states? The ones which are exactly linear under quantum operations.
Okay.
Now, if you take a process matrix and put different operations, maybe you get a different set.
Okay,
yeah.
Thanks. And the other quick question is, there was, I think, Emin showed that the set of process matrices is also the set of linear PCTCs, the post-selection closed timeline curve. Do you think that it is exactly the same as saying it is the set of linear 2 time states, or is there a difference?
Eamon? I don't.
I think there might be a work coming up from Villassini showing that this is the same thing.
Yes, so we have a work coming up.
Villassini will show it's the same thing in an upcoming publication.
So actually, the set of all 2 time states is equivalent mathematically to the set of all PCTCs, and in particular, the linear are also the same. So this is the upcoming work. This is the spoiler from the upcoming work with Ralph Silva and a student, Elliot.
Final question?
Yes. What do you mean by fundamental post-selection?
Okay, so in quantum theory, you postulate that you have a ray in the Hilbert space, like this psi1 hanging around, but then you may postulate that there is a state waiting for you, a final state of the universe, if you like, some people call this, that is already there.
So it's cosmological.
Pardon?
So it's a cosmological assumption. It's a
you can interpret it like this. In some sense.
I mean, there is post-selection final states in quantum cosmology, for example.
Sure, but here I'm not considering the state of the universe, right? When I write this psi1, I don't write the state of the universe. I don't know where this fundamental post-selection comes in. One way is cosmological, maybe. I don't know.
Okay, then let's thank Yelena again.